from earlier in from the solubility effects that I mentioned in lecture the other day. And the first one we're going to talk about is the common ion effect. And the common ion effect is a direct application of Le Chatelier's principle. So when we look at this, it should be kind of a review, but we're going to look at this in terms of solubility rather than in terms of acid-base equilibria. So what we can say about the common ion effect is that the solubility of a slightly soluble salt is decreased by the presence of a second solute that furnishes a common ion. And basically, what this statement right here is trying to tell us is that if I have a particular solid which reaches equilibrium with two ions in solution, if I add a larger concentration of one of those ions in solution, that solubility is going to be decreased when we compare it to water or an aqueous solution. So what we tend to observe is that if we would plot molar solubility on the y-axis, and we would plot the concentration of a common ion on the x-axis, we can assume that any given point right here would be an aqueous solution. As we add this complex ion, we're going to see a drastic decrease in the solubility until this effect eventually reaches equilibrium. So let's kind of do an example to illustrate what I've just shown here on the screen. So we're going to look at cadmium hydroxide, which is CdOH2 as a solid. It's going to be in equilibrium with cadmium 2 plus ions plus 2 OH minus ions. One of the things that I will tell you, when you see a question that asks you to predict or to explain something about solubility, you must always write out that solubility expression. Either that or have it ingrained in your mind when you read the particular problem. Because we need to figure out what's going on in that solution. What's happening? How can we manipulate it? How can we, try to make this particular salt either more soluble or less soluble? So here we have the equilibrium expression, and that's where your thinking needs to start. So we have an equilibrium expression. We can look at this in aqueous solution. So we'll set up our ice table. And initially, before any of the solid dissolves, we have a concentration of 0 for the cadmium 2 plus and the hydroxide ions. If we assume X moles of this solid dissolves, then the change in concentration is going to be plus X for the cadmium 2 plus and plus 2X for the hydroxide ion. That gives us an equilibrium concentration of X and 2X. If we wanted to figure out the molar solubility, because that's what's plotted over here on the left-hand side, we can look at the KSP should be equal to 4x to the third. The KSP for cadmium hydroxide is 2.26 times 10 to the minus 14. We can then calculate X to be 1.78 times 10 to the minus 5. And what this X value is the molar solubility of cadmium hydroxide in aqueous solution. So this is going to be our benchmark. We have a particular amount of cadmium hydroxide that is going to dissolve. So to illustrate this common ion effect, we need to figure out what happens to this solubility when you add a common ion. So what we're going to do is compare this aqueous solution solubility to a solution that is made to be 0.1 molar potassium hydroxide. So this means we have a concentration of 0.1 molar of hydroxide ion when we have to analyze this equilibrium expression. So again, we have to write out the CdOH2 solid in equilibrium with cadmium 2 plus ions plus 2 OH minus ions. We can set up an ice table. The cadmium hydroxide is a solid. It will not show up in that table. Our initial concentration of cadmium 2 plus is 0, but the initial concentration of the OH minus is not 0. It's 0.1 because we have a solution that is not aqueous anymore. It has potassium hydroxide in it. So this is going to dramatically affect our equilibrium concentration of the hydroxide ion. So the change in concentration is still going to be plus x and plus 2x. But our equilibrium concentration is going to be x for the cadmium 2 plus and 0.1 plus 2x for the hydroxide ion concentration. Yep.
And that has no effect, like when you were rewriting the equation after adding the potassium hydroxide, do you not want us to write it in?
Well, hold on, what was that question again?
Even though it's not going to have an effect, are we not supposed to like write in the dissociated potassium ion? Like in the equation?
So when we write an equilibrium expression, our equilibrium expression only includes the cadmium hydroxide solid and the cadmium 2 plus and the OH minus. Okay? Any other ion that you add, it will potentially present a dilution type problem, but you don't need to include those because they're spectator ions. So when we write this KSP expression, we can write it as the concentration of x times the concentration of 0.1 plus 2x, that quantity squared. Again, this is going to equal 2.26 times 10 to the minus 14. Since our k is so small, this is nice because we can make an approximation. And we can approximate that 0.1 plus 2x is going to be roughly equal to 0.1. So our 2.26 times 10 to the minus 14 is going to be equal to x times 0.1, that quantity squared. So when we go and solve for x, our x is going to equal 2.26 times 10 to the minus 12. So when we're comparing our solubility, or our molar solubility, this x right here is going to be the molar solubility of cadmium hydroxide in 0.1 molar potassium hydroxide solution. And see how much these values right here change by adding just a small concentration of our potassium hydroxide. Zach, you had your hand up over there?
Is there like a cutoff whenever you put the KSP is -5 and how big it is that we can beat that plus 2x?
So the question over here comes from when can we approximate that 0.1 plus 2x to be roughly equal to 0.1? When we're dealing with acids and bases, a lot of the K values range from 10 to the minus 2 to 10 to the minus 5. So they're a lot larger compared to these K values. I think the lead chloride, if you look on your KSP table, has a KSP of 10 to the minus 5. That's like by far the largest one. A lot of these that we're dealing with are 10 to the minus 10, 10 to the minus 14. Some of them are 10 to the minus 30, right? So pretty much in all cases here, we can make this approximation so we won't have to use the quadratic equation like we did back when we were talking with acids and bases. Okay? So you can pretty much assume that all these approximations are going to be valid. Just as a caution, you can go back and check. Here we have x being 2.26 times 10 to the minus 12. 0.1 plus 2 times that is still going to be 0.1. I mean, there's still 11 zeros between those two numbers. All right? So we're not as picky in this course as we were before about the approximations because these k values are so small. But the one thing that I want you to see in the common ion effect that comes into play is the fact that this expression down here is a lot different than this expression up here. Here we have 4x to the third, so when the equilibrium is established, it's going to be, you know, your x value, you're going to have to take it to the third power. Down here, we don't need to do that. And as a consequence, that molar solubility is much, 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 much lower. Here we have a factor of 10 to the 7th difference between the two molar solubilities. Okay? So we have a large difference, and we can see a large difference, and the common ion effect is, again, a direct application of the Chatelier's principle, and it's the same type of effect that you see when we talk about acids and bases. In this case, think about solids and their saturated ions in solution.